Hello everyone, welcome to our video presentation on Nikstore, an innovative online bookstore hosted on AWS Cloud Infrastructure. My name is Nikolya Fernando and alongside me is Nikitha Pieris. Today we'll walk you through how we designed, deployed and optimized Nikstore using Amazon Web Services to create a scalable, secure and cost-effective e-commerce platform for book lovers worldwide.
Nikstore offers a vast collection of books across all genres with features like secure payments, real-time stock management and personalized recommendations, all powered by AWS. Let's dive into the details. We used several AWS services including Amazon EC2 for hosting our web application, Amazon S3 for secure ebook and media storage, Amazon RDS for managing customer and order data, AWS IAM for strict access control and elastic load balancing and auto scaling for traffic management.
Let's get started with setting up our AWS environment. First, we try to attach the Amazon EC2 full access policy to our IAM role named lab role. However, as you can see in the second screenshot, we hit an access denied error when trying to attach the policy. This happened because our current user does not have permission to perform the IAM attach policy action.
Exactly. This means we need to request access from our AWS administrator to attach new policies to roles. Until then, we can only work with the permissions already granted to lab role, which seems to include Amazon EC2 container registry, Amazon EKS policies and some others.
Right. Moving on, once we have the right permissions, we can proceed to create our VPC. As shown in the third screenshot, we chose the option to create a VPC with additional resources, naming it Nikstore's VPC and specifying a CIDR block of 10.0.0.0.16. This gives us a large address space for our subnets.
Yes, and after creating the VPC, the console confirms all resources like subnets, internet gateway, route tables, and S3 endpoints were successfully created. Where we can see the fourth screenshot. This is crucial for our network to operate properly and to allow internet access where necessary.
Right, so next we head to the subset section. However, in the fifth screenshot, when we try to create a subnet, the VPC dropdown is empty. This likely means that we need to refresh the console or wait for the new VPC to fully propagate so that it appears in the list.
That makes sense. Once a VPC shows up, we can create subnets in different availability zones to ensure high availability for our applications. After setting up the subnets, the next step is managing the internet gateway, which allows instance in public subnets to access the internet.
Absolutely. The sixth screenshot shows two internet gateways, one of which we created for our VPC, Nikstore's IGW. It's currently detached, so we need to select Attach to VPC from the Actions menu, as shown in the seventh screenshot, to link it to our VPC.
Once attached, our VPC will be able to route traffic to and from the internet, which is key for public-facing resources. The 8th screenshot confirms that our VPC Nikstore VPC available with the CIDR block. DNS resolution is enabled, which is very important in internal name resolution.
Exactly. And from here, we can continue to create subnets, route tables and configure security groups to secure our environment. It's a step-by-step process, but getting the networking foundation right is crucial for any AWS deployment.
Agreed. With the VPC and related networking resources in place, we can move forward confidently with deploying our applications and services in a secure and scalable environment.
When we'll be walking through the process of setting up a NAT gateway and configuring our AWS infrastructure to ensure secure and efficient internet access for your private subnets. So let's start with the NAT gateway creation. So as you can see here, we've successfully allocated an elastic IP address, which is essential for the NAT gateway to have a fixed public IP. We named our gateway MyNatGateway1 and assigned it to our public subnet so it can route traffic properly.
Right. After setting up the NAT gateway, it's important to verify that it's created successfully. Here, we can see the NAT gateway is a pending state initial, which is normal. Once it's active, it will have a primary public IPv4 address and will be ready to route traffic from private subnets. Next, we need to ensure the routing tables are correctly configured. For the public route table, we add a route to the internet gateway for all outbound traffic, which you can see here with a destination 0.0.00 and target as the internet gateway.
Exactly. This allows instances in the public subnet to communicate with the internet now. For the private route table, which is associated with the private subnets, you should add a route directing internet-bound traffic to the NAT gateway instead of the internet gateway. Notice that in our setup, the private route table is linked to two subnets, meaning these private subnets will use the NAT gateway to access external resources securely without exposing their IPs.
Speaking of security, we also configure the security groups accordingly. Here's the security group of our web server instance, allowing HTTP and SSH to access for administration purposes. It's important to manage these rules carefully to avoid unauthorized access.
Now let's look at the EC2 instance running inside our private subnet. The instance is up and running, and we can connect it securely using the key pair we set up. This instance represents our web server hosting our Nix Store website, which you can see loaded successfully here in the browser. So let's look at the Elastic Block Store snapshots in AWS. Here you can see that we have created snapshots of the volumes associated with our environment. Snapshots are essentially point-in-time backups of our EBS volumes, allowing us to restore data if needed. For instance, the snapshot named Nix Store Backup is a key backup for our store's data. Maintaining these snapshots regularly is critical for disaster recovery and data durability.
Moving on to the RDS console, this screenshot shows us database instance named Nix Store DB. It's in available status, which means the database is up and running, ready to accept connections. We have chosen MySQL as our database engine hosted in the US East region. This managed service helps us to focus on more data rather than service maintenance.
Here we see the connectivity and security settings for the Nix Store DB. The endpoint and port 3306 are shown, which are used by clients to connect to the database. The database is made inside a specific VPC and subnet group, ensuring network isolation and security. The security group attached to the database controls access, and here is configured to restrict traffic, and the database being non-publicly accessible for enhanced security.
The next screenshot displays the subnet groups associated with the RDS instance. Subnet groups define which subnets the database can use within the VPC. This setup ensures that the database is launched in multiple subnets for availability and fault tolerance. Our subnet group is completely and corresponds with the VPC configured for the store environment.
Security groups are like virtual firewalls. The image shows the inbound rules for our RDS security group. The rules allow MySQL Aurora traffic on TCP port 3306 from trusted IP ranges. This ensures only authorized traffic can reach our database, protecting it from unauthorized access.
In this terminal session on an EC2 instance, we tested the connectivity to our RDS database using the nc command. Initially, it times out, but then it successfully connects on port 3306, indicating the security group and the network configurations are correct. After that, we log into the MySQL database as admin and confirm connection to the server.
Now, inside the MySQL shell, we create a books table with columns for the ID, title, author, and price. We insert sample records such as the Great Gatsby and 1984. These commands demonstrate how we can manipulate and store data within our RDS instance, making it ready for application use.
Here's the front end of our web application displaying the book catalog received from our database. We see the book titles, authors, and the prices formatted nicely on the web page. This proves that our backend database and forehand are successfully integrated with dynamic data fetching working as expected.
This is a fresh SSH session to our EC2 instance which acts as the web server. From here we manage our web application and database connections. The EC2 instance is part of our VPC and is used to run the web server that connects the RDS database.
Back in my SQL shell, we confirm our database contains 3 records now, with a never entry added named Nikitha. This shows how we can dynamically verify data in our cloud-hosted database, supporting ongoing application functionality.
Alright, so here we see our EC2 instance named Nix Store Web Server. It's running with instance ID 021E970EE453DAB69. It has a public IPv4 address and is passing all status checks. This is our main backend server. We created a target group called Nix Target Group with protocol HTTP on port 80 initially. No targets were registered here, but this group will direct traffic to our EC2 instances.
Next, we created an application load balancer named Nix Store ELB. It's internet facing, so it can serve public traffic and it configured to work without VPC. We selected the VPC and public subnets to ensure high availability across availability zones for the load balancer.
Here is the load balancers page showing Nix Store ELB. It's active and ready to handle traffic. We then created a launch template which will be used to launch instances with the required configuration.
Using the launch template, we created an auto-scaling group called Nix Store ASG. This group will automatically scale our instance between 2 and 6 based on demand. We also added tags to the auto-scaling group instance for easy identification and management.
Finally, back to the instances page. Now we have 3 running instances including our web server and 2 small instances all passing health checks. And here you can see that our target group has now has 2 healthy registered targets connected to the load balancer for smooth traffic distribution. Working on the Nix Store project really strengthened my practical skills in cloud computing. I focused on setting up the VPC and EC2 instances, and it was challenging to understand how public and private subnets, internet gateways and route tables all connected. But with some trial and error and support from AWS documentation, I managed to get it working. It taught me the value of persistence and careful planning in cloud infrastructure.
My main focus was on IAM, RDS and deploying web features. I initially struggled with the strict permission settings in IAM, which blocked some of my actions. Instead of giving up, I explored AWS forms and guide to fix the issues. This helps me understand how important security and access control are in cloud systems. Overall, this project helped me grow in both technical knowledge and problem solving.